in the basics. Then we are going to move on to the standards. Okay, so this is the transport layer security. Okay, which is also being used, in various standards in addition to the PKI, right, and digital signatures and so on. So here, this one is to set up a secure channel for any kind of communication. So before communication will start between two devices, you need to set up a secure channel, and that's done through transport layer security. Okay, it's at the transport layer level. Okay, so this is how it works. Let's say you have a server and a client, because obviously two people, devices want to talk to each other. So we are going to use the digital certificates. Okay, so we know what digital certificates are, right? Those are the ones of issued by the certificate authority, right? So each device will have their own digital certificate. So let's say we want to do server authentication. Okay, so and also the same way you can do the client authentication, right? So what will happen is the server is going to send its digital certificate, which is typically X.509. That's the standard for digital certificate, to the client. Okay, client is going to, and we know that certificate contains, information about the client and their public key, right? I gave you the structure of the certificate yesterday. We talked about that. Okay, so the client is going to verify that the certificate is valid, it's not expired, it's not, revoked. Okay, and also signature on the certificate is valid. That can be done using the public key, okay, of the server, right? And few other things in the certificate, domain name, that it's issued from a particular certificate authority. It's not, somebody just didn't copy it, right? So, and once it's verified, the handshake will start. And you can, if the client needs to verify, server need to verify the client's authentication, they can do the same thing. They can look at the client certificate and all. So once everything is verified, then the handshake will start. Okay, then there are a few things that can happen. They can exchange a secret key if the message is to be encrypted. Okay, so the secret key will be exchanged, because now they know client and server are both genuine, right? And then you can exchange the secret key, and then the data, transfer can start happening. Okay, so we already know about digital signatures. Okay, we talked about that. It's used in authenticating key exchange and proving ownership of the private key. Okay, right? So server certificate verify message. After sending its certificates, the server is going to sign a hash of a handshake message. It can be simple hello, right? So it's just a handshake message. Okay, and they will use their private key to do that. Okay, and the client will verify it using the public key, right? So the purpose is basically it proves that the server actually owns the private key. It's not somebody else. So it basically stops the attacks, man in the middle attack. Okay, that nothing has changed in the middle, right? So that's, and similarly, the client can do the same thing on their side. Okay, client may also send the certificate and sign the handshake message with the private key, and then the server obviously is going to verify that. Okay, so that's the handshake message. Okay, so once the handshake message is verified, right, with the digital signature, then the communication can start. Okay, and this is for client server communication, right? So this is, the start, and then digital signature, and then obviously client can do the same thing, then the process can start. Okay, let's just quickly do a quick walkthrough. This is something I had missed last time. Okay, I thought I give you, but you had the basics already done. We had talked about digital certificate and signature and all that stuff, right? Private keys and public keys. But let's go through a very quick example here. So let's say that, a substation, ID, and a control center want to talk to each other. Okay, so we want to do the key exchange, we want to do the authentication via digital signatures, and then the data transfer will happen once the keys are exchanged. So the secret key is exchanged. Okay, so control center is the client in this case, ID is the server. Okay, and they both have to support the same type of certificate standard. Okay, as well as the key exchanges and so on, right? Both have to have same type of softwares and algorithms there. Okay, so the step one in this process will be the key exchange. Okay, and let's say control center has, I have used small numbers obviously. Public key is 13. Okay, private key is 13. Let's say public key is 13 times something, could be anything. And let's call this P1, right? And similarly, the ID will have a private key, okay, let's say 25, and a public key is 25 times G, right? Call it P2. And both will exchange public keys, right? Control center will send the P1, ID will send the P2, okay? And each will compute a shared secret, right? And it's simply, you could have any algorithm to do that. So I simply said, okay, let's take the, private key, right? And public key. Private key of the server, the substation computer. So we get 325G, ID get 325G. So this is their shared secret key. This will be the one used for encryption and decryption, right? So so then you drive the encryption key using, using some kind of function. Okay, this is again the type of algorithm, and let's say that is k equal to 42. Okay, so authentication will start to happen. ID will send the same way that we talked about, will send the certificate, prove it's authentic, control center will verify it, right, using the public key. If valid, handshake is authenticated, but you could have the other way around, add also, that the server can verify that, and then and only then handshake will happen. It really depends. Sometimes they just do one, sometimes both have to verify, right? And then the secure communication will start to happen, and now they can, control center, let's say, sends the command, then it will be encrypted using the key that they both decided on, and then the encrypted data will be sent, and then it will be decrypted at the other end. So this is simply the transport layer security. Okay, now this is very commonly used in SCADA, and we will see when we talk about the standard where it is used, right? Now, although we are not going to discuss this in detail here because of the time, there are other types of security at different layers. At the IP layer also, we have a security mechanism. Okay, IPsec, for example, right? That's at the IP layer, which is used mostly in the BPNs, virtual private networks. Okay, and BPNs are set up. We will talk about that in the standards. Okay, but there is a lot of information available about VPN, so I don't think we need to go over that here. So at a different, and then there is even a security at the MAC level. Okay, MACsec is another level of security. Okay, those are mostly for the BPM. Okay, so this was a very quick information about the transport layer security. Any questions? And then I'm going to just show you actual, keys and so on, so you get an idea about that. Okay, any question about this? Good. This is something we had already done, just a little bit more explanation. Okay, so now I'm going to very quickly run few programs. I'll try to explain what they are and what they do. So you have to bear with me here. I have to set it up here. Oh no, this one. I'm just changing my directory so that I can run these files. So the first one is symmetric, right? Let's do. So I have this AES, which is a symmetric cryptography. Okay, AES is one type of algorithm that we had mentioned. Okay, so let's see what when we run this. It's basically what it does is it will generate the key. Okay, it will generate the key. There is the original message. I just included that this is a secret message. This is the encrypted message. So this is how it will look like, right? I don't know if you can see that, but then there is a decrypted message at the other end. Okay, so this is a very simple example of symmetric cryptography. Okay, so you generate the key, and then through TLS, you are going to share that key eventually, when both sides are talking to each other, or some other way you are going to share that key, and then at the other end, it will be decrypted. So this was one simple example of AES. Okay, but let's take a look at digital signatures. Okay, and encryption and decryption included in there. Okay, so you can have a message. Okay, sign it, encrypt it, send it to the other end. Okay, where your signature will be verified and it will be decrypted at the other end. Okay, so there are few steps in this one. Let me just show you the steps I'm going to use. Okay, so the first step is to generate the keys. Okay, you need to generate a private key. So I have written a program to generate keys. I'll show you how they will look like, but let's just run this command. You see that it says keys are saved, private key.pem and public key.pem. Okay, but let me show you how the keys look like. So if I go to my directory here, there should be a file named private key and a public key. See that private key? This is what it looks like, rather than 5 or 12 what we used, right? This is how the private key looks like, and this is using a algorithm called RSA, okay, which is very commonly used also. Okay, there are other algorithms that may be used, but this is how your whole key, private key, and similarly, we can take a look at the public key, which is obviously, you know, which will look similar. You know, it's kind of a gibberish basically, right? But right, this is a little bit smaller size public key, right? Again, using the same type of algorithm. Okay, just again to give you an idea how in reality, you know, these things look like. Okay, so and then what we are going to do is we are going to use the second step. We are going to encrypt a message. Okay, and if you see here in the line, the message is top secret. Okay, I have included that as a message. So I'll try to run that here. See, the message is top secret. It's going to be encrypted using those keys. Okay. And the encrypted message is going to go into the file encrypted.txt. Okay. So let's take a look at that, how that encrypted message looks like now. So there should be a file encrypted.txt. Yeah, right here. This is what that message looks like. Okay. So the top secret message has been encrypted using, you know, the key, right? That's how it looks like. So the next step is you can, let me just see, we can decrypt it back. Okay. So obviously when you encrypt, you're going to use your private key, right? And when somebody decrypts it, they're going to use your public key, right? So this will be done using the public key, which we have already created, right? So decrypt it. Let me just again run this very quickly. And it will go into decrypted.txt, right? So it's written. So if we see what is in the decrypted.txt, it should show up as a top secret message, right? There it is, right? So it's decrypted, okay? And right, and now we can see sign a message. Okay, so you are going to sign the message with a private key, right? And again, the message that is to be signed is top secret, right? So you can sign that, and the output file is signature.txt. So let's take a look. Signature.txt, signature.txt, right? So yeah, so this is the signed message. That's how it looks like. So it's again, you know, so this one, you know, so obviously at the other end, to verify the signature, you are going to use the public key. right? So the next one is verify the signature. Okay. Yeah, so it says signature is valid. Okay, now let's try to, let's say the message that we had, let's go back, the signature that we had, right? Let's say we change it, we play with this and change something, even small thing. Let's say make this AA, right? So I'm going to save this, and now let's run that command. This command to verify. Signature is invalid, right? So obviously it didn't verify that signature, right? So, and in the same way, I have few other things that we can do, and maybe we can come back to this depending on the time. So this is again demo of TLS that we just talked about, right? Again, using the certificates and so on, right? So we can come back to this, or we can, if you feel that you need to see some of these demos, we can go back to this, or during the lab time, we can do this, right? Yeah. So any questions on this? This was, again, just to demonstrate what we talked about. Yeah. Yeah. The size of the key can be changed so that you can specify in your algorithm. So um, so so we talked about the symmetric, right? So the key size, larger the key size there, harder it is to break. Whereas in this one, the key size does not matter much in the asymmetric, because the encryption happens through the algorithm. Not really the key size is not. The keys are needed, but size is not directly proportional to how difficult it will be to break it, right? So because it's based on the algorithm, right? Yeah, I just played with the signature. If somebody tampered with the message, they try to, let's say it was a opening a breaker, which was signed, right? And somebody say, okay, I'm going to now, tamper with that message, right? So as soon as you try to tamper, at the other end, it will not be verified, right? So that's what I was trying to demonstrate here. Okay. Any other questions? Okay. If there are no questions, we are going to move on to the standards and solutions. Yeah, that's right. RSA. No, not at both ends. This will be generated by the certificate authority. See, the keys are kept and generated by the certificate authority. Devices don't generate their keys. You have to be registered with the certificate authority. Public key infrastructure is all controlled by the certificate authority. I just generated so that we needed it here, right? I generated it using a program, but these ones will be generated by the certificate authority and kept. Public key will be available to anybody, doesn't matter who it is. Private key will be only with that particular device, okay? And in some cases, it may be stored right on the device. We talked about that yesterday, right? Or it has to be kept secret somehow, somewhere. right? And the only that particular device will know its private key. Nobody else will know the private key. Then you are in big trouble. Yeah. If somebody gets hold of the keys, and actually it did happen in one of the cases, it did happen. I think I can't remember what was the situation and where it did happen, but that will be a huge problem. If all your keys are gone, then you obviously you have nothing, here. So, but the thing is that you will monitor wherever keys are stored, you will monitor it, right? As soon as you know you're going to revoke all the keys, and right. So, right. Yeah, but that's again, you have to secure your keys.
Them certificate authority store the private key with them.
Yeah, maybe I can't hear you very well.
Hello, hello. Hello.
Yeah.
Certificate authority stores the public private key with them.
Certificate authority?
Stores the private key with them or not?
Yeah, so it depends what type of setup you have. As I said, sometimes the private keys are stored on the device itself. Okay. Sometimes you may have centrally stored, right? But the devices have to know their private keys somehow, right? Because if they're going to sign something, they have to, know their private keys. But the storage depends where you are going to store that. Okay. Also, sometimes it's a good idea to, change those keys periodically, right? You don't want to keep them same, so that, so it's just like your passwords. Okay. Yeah. Yeah. No, no, no. It depends on the. It depends. If you keep that, you will get the same encryption. Yeah, yeah, yeah. Obviously, yeah, because you are using the algorithm, right? So it will produce the same result. Yeah. But if the message changes, obviously, the encryption will change. It will be different. Sorry, sir. Yeah, because message hasn't changed. It will be the same, and it will produce the same encryption. Encryption won't change. If you keep, yeah, but to decrypt the message, you are going to, oh, okay, yeah, yeah. If you have only set number of messages, yeah, you can, obviously, you can make it faster, you know. Yes, yeah, yeah. Those strategies can be used again, and we may have to use that, especially for messages that need to be very fast. For example, tripping messages and so on, right? So there you may need to do that. Yeah. But for the asymmetric algorithm, it doesn't take very long. The algorithm can run very quickly, right? Yeah. Key generation. Oh, somebody forgets their private key. Yeah. No, you can't. You have to go to the certificate authority to get the keys. Yeah. They are the ones who are generating these keys. Yeah. Okay. Yeah. Yes. Yeah. So that's what I was saying. Sometimes, and the keys are stored right on the device. So if that's the case, then they can do that. Yeah, you could do that, because once it is stored there, that means it's kind of generated there. Yeah, yeah, because private key is your device's key, and device is the only one that's going to use it, right? Nobody else is going to use that. So that's, again, we are talking about various mechanisms. Yeah, you have to do that. You have to. So again, these are all various mechanisms, right, through which you can manage all your key infrastructure. Okay.
Private key can generated by only the certificate of they will issue. It can be done after the approval of CA.
CA. Yeah, your certificate authority has to be involved. Yeah.
But let's say CA is not in the loop.
Yeah.
Then there will be an issue.
Last question, sir. To verify this public key, private key, means to verify this communication, every time we have to, or only CA can verify this. So we need
The
internet connection.
are you talking about the certificates?
Yes.
Yeah, certificate is issued by the CA. We know
Yeah.
that, right?
Mm-hmm.
So, but it will be verified by the other end where you're trying to communicate to, right?
Okay. So
Yeah.
in that case, we need an internet connection. Otherwise, the keys should be saved on the device. That is the only possibility.
Yeah, but either way, you need the communication. It doesn't matter. So if, for example, even verifying the certificate, let's say you have a certificate and you are presenting that certificate to me, I have to verify using your public key,
Yes.
which I have to get from somewhere,
Okay.
right? And sometimes it's included in the certificate and I can use that, right? But I need that communication has to be always there, obviously. Yeah.
Yeah, for long distances, we are using 104. 104, we are using 104 for remote control center communication. For that, we are using TLS 1.3. For within substation, we are not using any type of encryption.
So
As
you
of
are
now.
talking about your particular situation.
Yes.
So let me understand. So you are trying to communicate long distance.
Yes.
Right. So you have to use the TLS in that case.
Yes. Yes. We are using TLS.
Yeah.
Yeah. So for that, to handshake to be complete.
Handshake to be, you need the communication.
Yes.
Yeah.
So we need to communicate with the CA to verify that.
No.
Okay.
You don't need to communicate with the CA to verify that. See, we went through the mechanism, how the steps will be done. CA is not involved. As long as you have the certificate issued by the CA that you can present to the other end.
Okay. Yes.
Yeah.
Yeah.
Right? Because your certificate has all the information about you. Other than the private key, it has the public key and so on, right? Right? And the other end can verify, right? Because you are going to sign that certificate with your private key, right? And the other end can verify by using your public key whether you actually signed it or not, right? And that public key is part of your certificate. So they already have the public key also, right? And you can do the same thing from the other end. If that's what both ends need to verify, they can go through the same process. right? Yeah. Yeah. System level, it again depends on the type of infrastructure you're going to set up, right? So somewhere they have to be stored. Yeah, so sometimes, as I said, private keys are stored on the devices itself, okay? And, somebody has to maintain these public and private keys and also revoke. We talked about what is the role of certificate authority. So the certificate authority has to store all that information somewhere, okay? Could be on a secured server, right? Yeah. So it again depends how you set up your. Yeah, so it's again, you so in case of the internet, we talked about who has the authority, right? So it has to be Google and all those, right? So they make sure that whatever they are storing is secure. In case of utility, can be a utility themselves, or it can be the vendor, the suppliers, ABB or Siemens or some of those companies, right? Yeah. Can CA? Yeah, yeah. CA is basically, yeah, you see that. So we had a intermediate CA, right? We talked about that. Yeah. So you can, again, it all depends how you want to set up your public key infrastructure. If you're comfortable with that, you can have an intermediate CA, which may have access only to the part of the whole database, right? Which only are required by that intermediate CA, right? You could do that. Can be done, yeah, can be done. But then again, you have to make sure that your intermediate CA is fully secure and all that, right? So, yeah, yeah. Huh? That's right. Yeah, yeah, yeah. Okay. I'm sorry, root. Um, so you're talking about, again, certificate authority. Offline or online? It has to be online, right? Because root CA has to be. Oh yeah. So if you have intermediate CA, then your root CA can be offline. That's what you are asking, right? Yes. Yeah. If you have, but intermediate has to be online, right? So this is again to protect, let's say you have, uh, root CA that has all the information, okay? Now, if that gets exposed, then you lost all the complete information. But you could have intermediate CAs that has only partial information, right? So that way you are basically dividing your risk in a way, right? So, okay, yeah. If somebody is, so they're simply accessing the data, right? So, yeah, but somehow you have to figure out that somebody has gotten into your system. They're not modifying, they're just, sniffing. It's a sniffing attack, basically. It's a sniffing attack. So they're just sniffing your data, right? Yeah. So you have to somehow find out that somebody has gotten into your access to your system. If they are not modifying anything, they are just sniffing it. Okay. Yeah. Okay, so I think we will move on to our next, otherwise we are going to be. Okay, so what we want to do is we want to look at the standards and solutions. Okay, yeah, before we do that, let's just look at okay, so I have to look at here. It's not showing? Both, yeah, so we have to. Yeah, but here also it's not showing. Yeah.
Is that this one is here?
No, it's not there. to provide for that particular standard. So we will take a look at this one. Okay. I'm not able to. Nope. Don't have the control here. Nope. Now it's okay.
He will change from there. He will change.
Oh, I can do that. You can leave it here. I will do that. So I have to change both of these. That's okay. I may be okay without the notes here. Yeah, so this is again just benefits of connectivity and then some risks that we have, right? So that's just the general information that I have. So let's get into directly into this standard. Okay. And the goal of this standard is to really define security measures for power system communication protocol. And this actually does, more than IEC 61850. Okay. Operational data, both at SCADA level, substation, as well as DER level. Okay. And secure management also. So it has multiple parts in this standard, and we will talk about that. Okay, and there is a relationship to other standards, as I said, the IEC 61850, as well as the SCADA standard. Okay. So we talked about the three pillars, right? Confidentiality, which is encryption, integrity, mainly digital signatures, right? Availability, right? We will talk about the IDS later on, and then authentication, okay? As well as it talks about role-based access, okay, which we haven't talked about yet, okay, which is extremely important. Also, we will talk about that, and also proof of origin and delivery, which is done by a digital signature. So once you signed it, a message, that means you are the one who are sending it, right? So the part three, sorry, 62.351.3. Okay, it mainly focuses on TCP IP based protocol, which is MMS in IEC 61850. You remember the upper layer, MMS layer. So it's basically this part of this standard part 3 focuses on that, and IEC 6870-5-104, which is the SCADA, okay, standard. We will talk about that standard. I have a very brief introduction to that particular standard. I'm not sure if this is the one that's used in India, but it's an IEC standard. Okay, and the main component, okay, now this is where what we have done will come handy, because we now understand what is TLS, what is digital signature, what is digital certificate. So the key technology it uses is transport layer security that we just talked about. Okay, so it will provide obviously the encryption, okay, which provides the confidentiality of data. It's going to provide the authentication by using the certificate, okay, that we talked about. It will provide the integrity because it's a signed message, okay. So where it is used, for example, secure SCADA to RTU, right? So you can, if you are doing SCADA to RTU message communication using this particular standard, okay? IEC 6870-5-104, which is the TCP/IP portion of that particular standard, okay? So obviously this is over the networks where you have TCP/IP standard. So this is the part 3 of this standard, okay, which is again based on TLS technology. And then there is part 4, which builds on part 3, okay. So it's securing the MMS client server communication, okay. IEC 61.8, part 8 of IEC 61.850. And again, this also uses TLS for transport layer, okay. And so at the MMS layer, it's going to authenticate the clients, the same TLS, okay. And then it's going, once authenticated is authenticated, then they can connect to the servers, basically, right? IEC 61. For example, if you have an engineering workstation which is trying to connect to your IEC 61.850 network, you have to go through that, okay, through the TLS. Okay, so that's part 3, part 4 of the standard, sorry, okay. Part 5 is mainly related to DNP3 and serial communication. So this standard is trying to cover various standards that are mostly used in the power industry. So DNP3 has both components, right? Serial communication, as well as the newer version actually has the networked communication, okay? So the challenge here is the protocols without TCP/IP, okay? So networked version uses the same as TLS, which is same like IEC 61.850, right? If you have a networked version of DNP3, you have. But if you have a serial version, then this standard, this particular part of the standard, it will define the application layer authentication, okay? So once it's authenticated, then master station can send control commands to DNP3. So that's the part 5 that defines that, okay? Now we will see how it provides the security. That's the part 6 of this standard, okay? I'm just giving you a very quick gist of all these standards. And later on, we will talk about the solutions, the complete solution, how using these standards and some of the other techniques, we can provide the complete solution for cybersecurity in power system and in substation. So as you know, IEC 61.850 goose and sampled values are not secure. So part 6 of this standard talks about this. And what is the challenge? The challenge is it's high speed, low latency, multicast communication, right? Both, well, goose is multicast, sampled value is not, okay? So digital signature is the one. So any goose message will be signed. We talked about that, right, earlier. And that will ensure the integrity and authenticity. There is no encryption, because encryption, decryption will take time. So you have to, maintain the real-time performance. No encryption, only digital signatures are done, right? And we will talk about this particular mechanism of virtual LANs, basically segmentation, dividing your network into various segments, right? So that you can basically reduce your risk, right? If one portion gets compromised, at least the other portions are okay, right? So virtual LAN segmentation, okay? So this is part 6 of the standard. It basically defines that. And part 7 is management. We haven't talked much about that yet, okay? So managing and monitoring the network and device security. Okay, this is part 7 of the standard. Actually, it's in some regulations, for example, NERC SIP, right, North American SIP, uh, they actually mandate that there be management and monitoring of the network, right? So it defines these technologies for various power systems. This is the part 7 of the standard, okay? And in order to even monitor, they use this particular protocol for communication, right? So you're basically monitoring your whole network, what's happening on the network itself. Okay, this is more the management part. So what are the benefits? Centralized security monitoring, breach malfunction detection, and secure configuration management, right? Those are the ones, right? So, so that's part 7 of this standard, particular standard. Okay, so this is the rule-based access. This is another solution that we will talk about. Okay, this is part 8 of this particular standard, IEC 62351. Okay, and part 8 basically defines how you will set up the role-based access rights. Okay, so depending on your role, you're going to get that amount of access, okay, to the system. So the principle is least privilege. Okay, depending on your role, you only get that privilege. Okay, that's the minimum you will get. That's it. Okay, you don't get access to anything else, and this sometimes is a problem. For example, the standard role, the operator may have a different access, engineer may have a different access, and administrator may have a different access. Sometimes all these roles, they have the same access. Okay, so role-based access. So permission is mapped to the roles. Who gets permission to what devices and to do what? It's based on the role. Okay, and obviously they use the mechanism for this certificate. We already talked about it. They use the digital certificate. So let's say I have a permission to open particular breaker. Then obviously I have to present my certificate, and at the other end, my certificate will be verified, and it will also be verified that I have the access, I have the role that gives me access to that particular breaker, and then and only then it will be open, right? So this is role-based access, and we will talk a little bit more about that when we talk about the solution. This is part 8 of the standard. So as you see, the standard covers quite a bit of ground. And then part 9 is the key management. So this is where we had a lot of questions already. So this standard defines that. Okay, so cryptographic key and certificate lifecycle management, right? That's part 9 of the standard. Okay, so it's obviously, we know it's critical for all these, certificates and TLS, as well as digital signatures, and it will include the public key infrastructure and certificate authority management. So the standard defines how and what you should be doing, right? And certificate enrollment and, revocation less secure key distribution, right? So, so utility can do that. They can manage, and they can, issue and revoke, and, all the certificates for all components. They can do that. So we had a fair bit of discussion on that. But the standard part 9 of this standard actually outlines how this should be done in that, right? And then part 12 is about the distributed energy resources. Yeah. Oh, these are various protocols. For we remember we talked about a few of these earlier when we were talking about the revocation lists. These are again various tools and mechanism of doing that. Yeah. Okay. And that's why I wanted my notes so that I can give you the full abbreviation. There are so many of those. I can't even remember what they are. Right. So maybe let me just tell you. Here I am 9. No, I can't do that. Let me just okay. Let's see. Okay, here we go. So let me just explain to you. These are yeah, no, I don't have. These are all protocols and mechanism of certificate enrollment. For example, I think we talked about EST earlier. Okay, these are certificate revocation lists that and these are again the communication protocols that you use for communicating, right? So all these tools are available actually to set up that infrastructure, right? Okay, so 12 is DER, okay? And the issue here is that there are so many and they are dispersed, devices, right? And they have varying ownership and varying security, right? Everyone is, different level, okay? And also there is a public network communication. They usually communicate over public networks, these DERs, okay? So it's basically applying the same principles to DER, but the big problem, so it's obviously TLS, it's applying and using all these digital certificates, but the big problem is just the sheer volume of these, okay? You have many of these DERs, you could have, let's say, at least in Canada, every house can be a DER, right? I'm not sure about India's situation. Every house can set up solar panels on their roof and start supplying power to the grid. So, every house can be a DER. So now you can just imagine how many DERs we are talking about and how would you secure that? Because they all communicate, right? And over the public network. So part 12 of this standard tries to, uh, identify or specify how you will provide security for DERs. And again, the technology used is the TLS that we talked about, right? So every time they want to communicate, they have to prove that it's really, they have to prove their identity and that they are authentic. So, but even managing their certificates and so on, it's actually a huge task also. But part 12 of the standard tries to do that. Okay. So this is again, summary of that. What are various parts doing here? Okay. And what are the key communications that we have, right? SCADA to gateway is 6875-104. HMI to IED is MMS, which is client server communication. IED to IED is Goose, okay? And then merging unit to IED is sampled values, right? And what are the various parts? We talked about that part 3 and 4 is TLS, MMS authentication, client server communication. Part 6 is digital signature for the goose sampled values as well if you want to do that. Okay, usually they don't. Part 8 is the role-based access, right? Control, how to do that. Part 9 is the certificate management. So it tries to cover a lot of ground. Okay, so these are again few of the cases and how and what part of IEC 62351 will come into action. Okay, so let's say somebody tries to send a fake goose message to trip a breaker. Without that, there is no security. Without IEC 62351-6, there is no security. With that, obviously the signature will be invalid on the fake goose, okay? And message will be discarded and there will be an alarm raised that somebody is trying to hack into the system, okay? So that's just one scenario that I have. And then similarly, SCADA, interception and manipulation of SCADA commands/data. Okay, so without that, obviously, it's vulnerable to injection and spying, all that data. Okay, with this, we have TLS. Okay, mutual authentication. It's encrypted, integrity checked message. So basically, we will attack, block the attacker, and communication will be. So it's basically transport layer security, right? That's the part 3 of the standard, right? So this is with the uh, virtual power plant, okay? So part 3 and 5, again, using TLS also, right? And part 9 is the infrastructure, how to set up the public key infrastructure. So it could be a scalable public key infrastructure. So as the new DERs come online, you could basically scale that infrastructure, right? So part 9 tries to tell that, and part 8 is the role-based access control. So you basically every DER can be given a role, okay, what they can do, okay, and most of the time they can only send the information. Their power production, right, information, because that's what the utility will need. Okay, so they can't do anything else, for example, right? So basically their role can be very much clarified, and there may be some DERs which are allowed to say trip the main breaker, where point of coupling breaker, right? So you can provide them that kind of role, right? And part 14 is the management, okay, central security logging, okay. So those are again various scenarios for the DERs we can have. And there is part 14, which is the security event logging, okay. So we will talk about the SIEMs, real-time SIEMs, okay, which is again management system, right? And so this part 14 is basically what to log, how to log, okay? So that you can go back, if there was a attack, you can go back and do the forensic analysis, that why that attack happened and where attack happened and so on, right? So that's part 14. It's actually very comprehensive standard that we have, okay? And I think this is again the PKI infrastructure, okay, which is essential for this standard, okay, and it's required for various parts that we talked about, okay, and the components, right? Certificate authority, revocation authority, certificate storage, okay, the lists that we maintain, right? And The big challenge is basically it has to be secureable, and security, we talked about the PKI security itself, which is very essential. Okay, so it does issue the certificates to IEDs, gateways, as well as clients, right? So that's again part 14, sorry, the role of PKI. Okay, so these are the challenges in implementing, and we talked about the legacy systems, right? Because they will lack the hardware for modern security. We way back, I think almost 10 years ago, we did some work for a French company on, doing the cybersecurity, and the hardware did not have the capability to implement the algorithm. So we ended up actually attaching additional hardware to the device, which was outside, right? So legacy systems, they lack that hardware. And if somebody wants to start a company, good business to get into right now. Okay. Start building hardware which will go attached to the devices and then implement the cybersecurity system. Okay. PKI complexity, we talked about that. That's actually a huge problem, right? So especially with DERs and the number of, devices as they increase. So PKI setting up is a big, challenge. This is actually another problem I think I mentioned last time. There is still work that need to be done. We can implement this IEC 62351, say in IEC 61 on top of IEC 61850. But how does it affect the performance of IEC 61850? We don't know. That's actually a challenge. Okay, and it must not affect the real-time performance of that. Interoperability, that's another one. Skill gap, um, right? Patch management, it's very difficult in operational environments, and also it's very much cultural. Every time a new version comes, engineers are very reluctant to put that on because it may mess up something else, right? So they are happy with the older version. They keep it and they say, we are happy with this, but it may be vulnerable from the cybersecurity point of view, right? So that's another one. The cost can be significant upfront for implementing all these security mechanisms in there, right? So those are again some of the hurdles. Okay. So this is, we will talk about in the solutions, defense in depth, okay, which basically layered approach to cybersecurity. Okay. When we talk about the solutions, that's next what we will talk about. Okay. So, and also all these steps we are going to talk about. Okay. IC 62443 is a standard which is mainly for general power system. Okay, we will talk about that, and some of the solutions we will talk, where you do the risk assessment. So basically you provide the security levels. You start with security level 0, which is basically minimal risk, all the way to security level 5, which is very high risk. So you identify, various, and then you provide the security accordingly, right? So you identify the assets, you identify the paths, and you prioritize them based on the risk. Okay. Um, and obviously develop the security policy. Defense in depth, we will talk about that. So segmentation, I already mentioned, firewalls, intrusion detection system. We will talk about those 3 components for sure. And then PKI, I'm not going to talk, at least here. We will not have time to, do more on PKI than what we have already mentioned. Okay. These are again some of the best practices that some of the general things that we already mentioned, right? So I'm going to leave this one with you. Yeah, this is the performance testing. Okay, whether you are IC 62351 compliant or not. So this is an interesting thing that doesn't matter which standards you look at, more or less principally they are the same. I'm not sure about the Indian standards, but you probably they also talk about some of these things. I know NERC-CEP, those are regulations, they are not standard. So NERC-CEP, for example, basically tells you what you need. It doesn't tell you how you will achieve it. Whereas some of these standards, IC standards, they tell you how to achieve it. But for example, you should use TLS and so on. So I'm not sure about Indian standards. Are they regulations? Because there is a difference between a regulation and a standard. Okay, standard will basically tell you how to do things, how to achieve it. Regulation will tell you that you must have this, you must meet that requirement, right? So IEC 61850, if you want to secure that, you need that one. Okay, so these are again some of the standards I was talking about. Okay, we will talk about this one. I'm not going to talk about NERC-CEP, which is more regulatory requirement, and also it's more North American. It's not probably applicable in the Indian context, but there may be a similar one for the Indian context. But again, as I said, they all look almost the same, mostly in principle. So we will talk about 62443 next. Okay. So the future focus of this one will be this standard. Obviously, they're going to keep updating it. Will be 5G IoT microgrids. Okay, enhanced DR microgrid security. Right now, it has something. PKI automation. That's another one. I think eventually the tools will come, which will make it easier to set up that infrastructure and monitor it and so on, right? And then quantum resistant crypto, especially for asymmetric cryptography, because the algorithm based, because if you have enough computing power, you can break it. Okay, and artificial intelligence and machine learning, threat detection. Also, there is some work going on that. We will talk about rule-based detection versus AI machine learning based detection. I have one presentation on that. We will talk about that. And then expanded testing and certification of that. Okay. This is again some of the benefits. Okay, I'm going to leave this presentation with you. So this is important, more from the cultural side, that everyone should be involved in, the culture of cybersecurity, right? Starting with the leadership, engineers, security staff, procurement, everyone. It's at every level. It should be like that. Okay. So IEC 62351 that we talked about, it actually covers quite a bit, right? SCADA, IEC 61850, DNP3, DERs, okay? And the principles, we talked about that, right? And so it will provide, once implemented, it's going to provide some, good cybersecurity. So are we stopping here or continuing? We will stop. Okay. So next I have is the solutions. Okay. So we will talk about IEC 62443 standard and some of the solutions, not only within that standard, but even in general. So we will talk about the segmentation. We will talk about the data diodes. Okay. We will talk more about the role-based access control. Okay. So some of those solutions we will talk about. Okay. So we will stop here for now.